But you should be saying, well, can you show me something new, Miss Naylor? I came to school today. What we're going to do is we're going to do some harder integrals. And what that really means is we're going to do some problems that have some harder antiderivatives. And there might be some other things that we end up doing with area, which in fact we will. So you're going to feel like we're kind of still talking about the same thing. That's what the book does. It kind of revisits and goes over it some more. But again, most of the problems I'm doing, there's something a little trickier about them. And so let us begin. Now, you do want to realize that when you see the integral of 1 over x dx from 1 to 3, when you see that, okay, that you realize, okay, this is like a good old integral. It's actually called a definite integral. Definite just means that we end up with a number answer. Of course, the number answer is really the area, so don't forget all that. It is still true. It's just that we're going to invoke some antiderivatives that might be a little bit uncommon. So let's find capital F of x. Now, I actually have sprinkled this problem into some other examples. That is the antiderivative of 1 over x. Okay, this is just one of those straight up, you kind of memorize it or reverse memorize it from last half a year. And you say to yourself, whose derivative is 1 over x? Whose derivative is 1 over x? And the answer is ln. So that means the antiderivative is ln of x. Maybe you noticed that the book used some absolute value symbols. That's at one point when you saw this before. Yeah, that's because you can't do the log of a negative number. So technically those absolute value symbols are there. It's not really a big deal this year because we're never going to end up with a negative number, but I'll put them there in case you're wondering about that. Okay, hey, don't forget it's b minus a. That means it's f of 3 minus f of 1. And here we have the ability to plug in without a calculator. So without a calculator, we could say the ln of 3. If we plug it in with the calculator, then we could change that into a decimal. Somebody says, well, which way do you want me to do it? I kind of want you to be obviously comfortable with both. Okay, so without a calculator, with a calculator. ln of 1. This would be a little more of an algebra idea, but let's make your algebra teacher happy. There's something mathematical about this. And I think if some of us are honest, we would say, yeah, I'm not really sure I remember what that is. Let me remind you that the ln of 1, or for that matter, the ln of anything, is really thinking about e to what power equals 1. So the answer to this problem is an exponent. It's e to what power equals 1. Well, actually, if you think about it, a certain power will always give you the number 1, whether it's e or whether it's any base. And that certain power is 0. That's a helpful little hint. That's a helpful little math idea that the ln of 1 is always equal to 0 because the exponent is 0. All right, so would I expect you to simplify this to be just the ln of 3? Yeah. I don't want to see you write as your final answer minus the ln of 1 because I expect that you made a little connection at that 0. Okay. ln. What else do we have here? Perfect. I'm glad that I thought about this because it'll allow us to have a little conversation about how to handle not 1 over x, but 1 over x squared. 1 over x squared. Just so you know, what I'm doing here is taking you down a little like fraction path. It's a little fraction path. We have 1 over x, but now I have 1 over x squared. Okay, now if that's kind of making you like panic a little bit, I'm going to show you, but make sure that next time that you're aware of this, that ln only works for 1 over x. ln only works for 1 over x. I told you there might be a time where I stop doing this. I don't know if that time will be the last day of the year because I'll do whatever we got to do to help you guys learn how to interpret. Now, you realize what's happening here? We're interpreting the fraction as a negative exponent. Okay, why would I do that? Well, because it's very easy to add and divide thinking of it as a negative exponent. Okay, so what I did in yellow right there is the power rule, the reverse power rule, but I had to think of it as a negative exponent before I add and then divide by the new exponent. Now, are you guys comfortable? Are you ready to kind of skip a little bit of the simplifying and realize that my final antiderivative is going to come out to be negative 1 over x. I flipped the x back down to the bottom. Okay, it was officially to the first power. It actually was officially to the negative first power, but we flipped it down to the bottom to make it positive first power, and then we're going to get rid of that. Okay, just kind of pausing because sometimes somebody will wonder, why can't you do that for this one? I'll be that somebody. If you're wondering what it was that somebody might have asked, why can't you think of this one as x to the negative 1? Well, now's a great time to realize this. Why can't I think of this one as x to the negative 1? Why can't I add to that and divide by, and that's why. Okay, 1 over x is special. It has to be an ln. It's the rule, but it's because you can't use the power rule. You would end up dividing by 0. Anything else, you're allowed to divide. Okay, you'll realize that fractions are something that we're going to keep talking about. Like, we're not done with fractions just with these two problems. It becomes a major focus of antiderivatives, just to be quite honest with you. Okay, fractions become a major focus of antiderivatives. Hey, be careful. I don't know if you're just kind of copying. I don't know if you're actually thinking. I would say without a calculator, we want to very carefully subtract. Without a calculator, we want to very carefully subtract. So we end up here with a whole bunch of negatives. But I think if we think about it, we all know that negative 1/3 plus 1 is 2/3. Okay, so, but we do have to be careful and trust the subtraction, even with the negatives. Anything that happened here? Okay, because I'm going to keep this train rolling. It's a fraction train right now. And we're going to do, I guess I mix things up a little bit, but I'm going to stick with the fraction theme. And now we're going to do the antiderivative of 1 over 1 plus x squared. It's actually the integral from 1 to 0 of 1 over 1 plus x squared. Okay, now, just so you get the idea, 1 over x is ln, and it's the only one. 1 over x squared, okay, I can think of that as a negative exponent. But now it's almost like I'm adding more to it, and we want to realize that this is a different antiderivative. Sometimes you realize it just because you recognize it from the first half of the year. If you don't recognize it, that's why we're kind of going over it to get you to that point. What are we supposed to be recognizing? Something out there has a derivative of 1 over 1 plus x squared. Something has a derivative of 1 over 1 plus x squared. And that something is inverse of sine. So we hear the inverse of sine, and you're definitely like in the right section. You're definitely in the right section. Tangent. Yeah. Okay. So inverse tangent is how we antiderive 1 over 1 plus x squared. All right. Now I'm not going to kind of keep saying it, but I'll just say it one more time that we have a lot to talk about with fractions. These three problems just kind of scratch the surface. We actually will talk about them quite a bit in the next chapter. So stay tuned. If you would be doing this problem on your own, I hope you would be aware that f of 0 is actually the f of b. It kind of seems like it's backwards. Yeah, it is kind of backwards, which is why our answer is going to come out to be the opposite. I might be giving away a little bit of the secret here, but if you plug in 0, you actually get 0. If you plug in 1, you don't get something I would expect you to know without a calculator. I had to take a peek, but it does come out to be 0.785 with a couple decimals there. But the main thing here is that you end up with a negative answer. As I hope you're going to do 0 minus 785. 0 minus 785. Okay. We just changed the order. We actually went from 1 to 0. We sort of went backwards. Let's see, just kind of looking over my notes here. Let's move away from fractions. I think we've done enough of that, but I'm going to use this space to talk about the antiderivative of something with an e to the x. So we're going to go -2 to 7 of 4 e to the x. Now, there's a couple different things we could do here. I think in the end, you'll say that it's easy if you're already wondering, yes. But I'm going to take this coefficient. I just kind of want to show you, because there's a time or two where this is helpful, that you guys realize that a coefficient, based on the rules that we talked about, is able to kind of park itself outside of the integral. A lot of kids will just kind of mentally think about that, but I'm obviously writing it so I can show you this time. Because what we want to think about is really the integral of the main function of e to the x. And that's the part where I hope that it seems easy to you, because the antiderivative of e to the x also just goes back to e to the x. Remember, e to the x is its own derivative, which means that e to the x is its own antiderivative. Now, could you write down 4 e to the x? You could. Like, if you don't want to make sure you don't lose that 4, I'm actually going to not write the 4 down, since I technically kind of pulled it out, and I'm just going to make sure I don't forget about it in the last step. But basically, don't forget about the 4 either way you decide to do it. Okay, nothing too fancy here. We're just going to plug in 7, and we're going to plug in -2. It's kind of the same song and dance. If I had a calculator, I would expect you to be simplifying that. If I didn't have a calculator, you could just kind of leave it as is. What I'm going to do, though, is pretend that I have a calculator, and I'm going to go ahead and simplify in my last step. And this is kind of where I want to meet you and make sure you guys understand that what I'm showing you is completely fine, where the 4 is really just outside of my subtraction. So we're going to subtract e to the 7 and e to the -2. But again, the 4 is not forgotten, and I can just kind of park it in front of that. Okay, and again, if this was on a calculator part of a test, it would be expected that you would basically put it in your calculator. It's not really that fancy, but put that in there and make sure you can get 4,386. That is a rather large answer if you think about the kind of answers we've been getting in the last week or so. And it just gives us an opportunity to remember what's really going on here. And that is, we're finding the area of an exponential graph. And this exponential graph has even been multiplied by 4. So this exponential graph is going to get very large very quickly. I can't draw it to scale. but get my gist here that the area from -2 to 7 is huge, okay, because our graph is huge. Okay, so it kind of fits with what we would expect if we at least think about what we would expect there. I want to do one more integral. Let's see how far we get with it. And it kind of piggybacks off of e to the x. But this time it's 4 to the x. 4 to the x. And I hope you realize that it piggybacks because it's exponential. When something's exponential, it's got a special antiderivative. And that special antiderivative is the same, just like the derivative is the same. With a little fine print on this one, are you kind of saying, wait a minute, I thought 4 to the x had some type of extra, okay, and it does. Back in derivative land, you guys would have multiplied by the ln. Now that we're in antiderivative land, we're going to divide by the ln. You'll catch on. You'll see that those extra steps where we once would have multiplied now just become a division problem. So we're going to divide by the ln of 4. And what that's doing is it's reversing the derivative rule. Okay, now we actually will talk more about that. I mean, I honestly just kind of threw that in, but it's just reversing the rules from the first half of the year. I'm being a little lazy here, but I'm saying to you that, hey, you could do that. I mean, we're just going to plug in 5, we're just going to plug in 3 and subtract it. I don't need to write that down 3 times. I can just write it down 1 time. All right, that will come out to 692. Make sure that you can do that on a calculator. I assume that you can, but so that I can show you the answer as an actual value. Make sure when you take notes that you write out, if you need to, the extra things that I did here, such as dividing by the ln. It might be something you write out in words. Okay, I have to divide by the ln of the base to reverse the rule from the first half of the year. We'll have one more intriguing problem, but definitely we'll do that after the break.